So thanks. Yeah, my name's Raichu. I'm one of the people who occasionally hack on the Idris compiler. And today I'm going to talk a little bit about programming with dependent types in Idris. So this talk is for people who don't really know what dependent types are and are curious about it. If you know what coq is or agda, then you will be probably bored. So yeah, I can't help it. Maybe there is something new for you. Who knows? So I will be talking about, obviously, dependent types and a thing that's called the Curry-Howard correspondence. One question, is this large enough? No? Okay, let's make it bigger. Better? Okay. So a thing that's called the Curry-Howard correspondence, which is, in my opinion, a very powerful mental model to reason about types as propositions. So we'll introduce that, and I will talk a little bit about constructive logic and how we can model this in the type system, so we can have more expressive types. I'll do a little bit of live coding, and hopefully everything will work out right. I don't know, sometimes things fail, so please don't laugh at me. And in the end, I will talk about effects and type providers. So Idris is a purely functional programming language. Therefore, we have to have some mechanism to deal with side effects, stuff like I/O, writing to files, communicating with the outside world, stuff like that. And we reflect that in the type system. And another thing is that, which is a pretty nice thing, is type providers. So we can do side effects on the type level. That might sound a little bit weird if you work with languages like C++ or other ones. Why should we have type system effects on the type level? But I hope I can convince you that this is a pretty nice thing to have. So what is Idris? Idris is a purely functional programming language that is developed by Edwin Brady. It's developed on GitHub. And so you can download the code, go crazy with it, send pull requests. That's what I did. It's a lot of fun. And it's currently intended as a research tool. So please don't use this in production. I've seen people who wanted to do that. I wanted to do that too, but you will figure out pretty quickly that you shouldn't do it. So yeah, it's a purely functional programming language. If you're familiar with Haskell or similar languages, it will feel pretty much at home to you. Of course, it's dependently typed. This is why we're interested in it. And the syntax is pretty close to Haskell. So some minute differences here and there. Of course, different semantics, but we're not going to talk about that too much here. What I find particularly appealing about the language is that it focuses on general purpose programming. So if you've got a system like coq or agda, it's more like a proof assistant. So you want to prove mathematical theorems or theorems about your software in coq or agda, but you don't really want to write a web server or similar stuff in that. That gets a little bit hairy. So this is actually one of the major selling points of Idris. In fact, these slides are written in Idris. They're compiled to JavaScript. That's a project I've been working on for a couple of years now. So you can try it out and write some JavaScript web applications or Node.js if you don't want to write pure JavaScript, which is, don't want to. So another thing that's pretty interesting is totality checking. So we can check if an algorithm actually terminates. That might sound a little weird as well, because halting problem. But if we don't have things like general recursion and just reduce ourselves to use primitive recursion, then we can actually prove that an algorithm terminates. We also have interactive proving with tactics. I'm not going to talk about that, but it's there. Obviously, we have a lot less tactics than coq, which has an insane amount of tactics. So what's the motivation? Why do we want more expressive type systems? Because there are a lot of very exciting type systems out there. So I gotta make this smaller, but only for this slide, excuse me. So types are a very, very effective way to keep program behavior in check. So we can guarantee that some things don't happen at runtime when our type system is, well, checking all these things. So you gotta have a function that you can guarantee that this function only gets an integer and not a string. That's pretty much the least thing a type system can do for you, but it's something. So when you have a very powerful programming language, so this is not Idris, this is C++, which has a very, very powerful type system. The template system by itself is Turing complete. It's completely insane. And so in this example, I'm just trying to model a conditional branch, something like if then else on the type level. Might seem a little bit contrived, but we'll get to an example where this is actually a useful thing to do. So you can see this is if then else is a pretty simple thing, but just to have it on the type level, we got to write this weird code over there. And that leads to a very interesting observation, that when you are programming in a statically typed programming language, you're usually working in two different languages. So you're working in the value language that you program most of the time in. So you write all your programs on the value level. And you've got the type level language that is used to program on your type level. And that's a completely different language. You have to learn two languages. You get two for the price of one, which is not very good because you have to duplicate a lot of stuff that you want to reuse on the type level, like this conditional branch. So we want to unify that. We just want to work with terms. And that is something where dependent types become quite handy, especially Idris. So what are dependent types? This is a little bit of a watered down view of what dependent types are. This is not like the full-blown whatever, lambda cube, yada, yada, yada stuff. So this is just very, very simple. If you want to know the whole story, read up on the lambda cube, on stuff like sorts and kinds. But I just want to give you a basic idea of what this is. And first of all, we got to talk about what a dependency is. So we can have values that depend on values. That's a pretty simple thing. We do that all the time. That's a function. So we can write a function. We could put a value into that, and we get a result. And the result depends on the value that we feed into the function. That's a very simple function over there. That's the increment function. It just takes a natural number and gives us a natural number. It gives us the successor. You can see that up there, this is, excuse me. So this is the type signature. I'm gonna make this a little bit larger. So I hope this is better. And this is the implementation. So it just takes an argument x, increments it by 1. So very simple function. Another thing that might be interesting to you if you don't know programming languages like Haskell, we do function application just by saying nothing. So no parentheses. This is function application. So normally you write f, parents, whatever. And we don't do it that way. So that's some sort of dependency that we want to have. We want to have values that depend on values, obviously. So another thing that might be interesting is we want to take types to values. So think about the identity function. The identity function it just does nothing. It just takes a value and returns the value unmodified. So when you have a lot of types, you have to come up with a lot of different implementations of the identity function, which is pretty boring. So you want to write one identity function that binds them all. So you want to have a type as an argument, and then it returns a function that can deal with these things. So in this case, we just take type A as an argument, and we return a function, which is a value, from A to A. So here we're using that. So it takes nat. Nat is a type of natural numbers, which is just 0, 1, 2, 3, yada, yada. And we return it unmodified. So what's interesting about this is that you can see we do type application just the same way as we're doing it with values. So there's something weird going on. If you've got a programming language like C++, you have these angle brackets, or Scala, you've got square brackets to do type application. Here, this just feels like a value. We're starting to get into the realm of what Idris is really about. So another example is just the same thing with strings. So another dependency that we want to have is types that depend on types. So think about data structures. So this is a linear list, and we want to build a linear list for every type. So list is a type constructor. It takes a type and it returns a new type. So it can take list, feed in string, and you get a list of string. And this type has two constructors. It has nil, which is just the empty list, and this thing is pronounced cons. We can take a value, take a list, put the value in front of it, and we get a new list. So we're inductively generating that list. So here's an example. We just have the list 1, 2, 3, 4, and we end with the empty list. That's a little bit clunky to write because we're using this special kind of syntax over there. We can use this very convenient list syntax to express that. So this is constructor overloading. We can do that for pretty much a lot of things. So in case you might notice this little single quote, this is just part of the identifier. This is nothing special. This is just so that I don't name clash with the actual list in the prelude. So yeah, now we've got 3 different kinds of dependencies. So there's just one thing missing, and that's the thing that you're missing in most of the programming languages, where you can take values to types. That's the new thing. This is what we mean when we talk about dependent types. We can have types that depend on values. So this is a string vector, and this vector is it's basically a list, but with the length in the type. So we have additional information in our type that says, okay, this vector is of length 4 or whatever. So obviously the empty vector is length 0, and the cons case, it takes a string vector of length n, and what we get is a string vector of length 1 plus n. And what's interesting about this is not a special type level plus. This is the same plus that we're using on the value level. So we've got a lot of reuse here. So whenever we've got a function that we can use on the value level, we can use that on the type level, as long as it's total and, yeah. So this is just an example. It's a string vector of length 4. I have 4 elements. If I were to delete one of these elements, it obviously wouldn't compile anymore. It would complain, hey, these lengths don't match up. Okay, this is too large. So, we can have a cake and eat it too. We can build a vector that is generic. So this is just the same thing. String vector isn't very, very useful because we can only put strings in there. So we don't want that. We want a vector for everything. And we also have that in Prelude. So this is a vector. This has got the same constructors as the list before. It has the empty vector with length 1. We also got cons. This is the same story. So now let's implement something that uses that. And in this case, we want to implement the append function. So append takes 2 vectors, a vector of length n and a vector of length m. And the result is a vector of length n plus m. So the type tells us a lot of what's going on here. It's a little bit different like append for list, where we just take list A, list A, list A. What does it do? I don't know. Could just throw away one of the lists. So here we are implementing this function. In case the left-hand side is the empty vector, excuse me, we just return y's. If it's a cons case, we just take the front element, we put it at the front, and we call append recursively. So we just go through the list, put them together, and voila. So here are 2 vectors, one with length 4, another one with length 4. We put them together. Obviously, higher mathematics, length 8. And that compiles. Great. So okay, that's the view, what dependent types are, what we can do with them. And now let's put them to use. And yeah, I want to talk about the Curry-Howard correspondence, which, well, it brings us into the land of logic. So there are a lot of logical connectors out there, and or not, whatever. And they have well, a corresponding type on the in the type land. So when we look at something like this looks very weird. So this is a type with numbers and an equal sign. So we call this type propositional equality, and we can only construct it if the 2 values on this equal sign are the same thing. Obviously, there are, by definition, 23 equals 23, so we can construct it. This is a comment. This is just a little pseudocode that I put up there, so you can imagine how this looks like. So it takes 2 arguments, something A, B, and we can construct this if both sides are equal. And what's interesting about this is that 23 equals 23 is a logical proposition. So we say this, and we're going to prove that. And whenever we write a program that satisfies this type, we've got a proof. So a proof is a program is a proof. It's not just a simple program. We can really use programs as proofs. And this gives us a lot of interesting possibilities when we want to do something like test-driven development. We call it type-driven development where I come from. So you can really write types that do an exhaustive check. So you can say for all this holds, for all values of whatever. This is a lot better than just a test, which is pretty much an anecdote. So I know some values where this works out. And you can do this in an exhaustive way. So since we've got logic, we want to have something like a truth value. This is a very trivial case. So we call this type unit, and it just has one constructor. So it's always true. Whenever I say I want some value of unit, here is the proof. It's just a simple empty tuple. We won't be using that, but just for the sake of completeness. Obviously, we want to have a notion of what's false. So I said that whenever we find a program that implements a type signature, that's a proof. So when we don't have a proof, then this thing has got to be false. It's an empty type. We call it an uninhabited type. So void has no constructors. We shouldn't be able to construct that. Sometimes there are bugs in the compiler. I think recently the Coq people found something where they could prove false. Happens all the time. It's software. It still fails, but it's pretty early. So it's research. Yay. So okay, this is the empty type. One have another thing which is called conjunction. So when I want to prove A and B are true, I want to give a construction for that. And so once again, I'm using propositional equality there. These things are trivially true. 23 equals 23, yada. And this is the proof for it. So when we want to prove that two things are true, just give me two proofs. Give me the two proofs and put them together in a tuple. So where it's and, there is or. We've got something that's called the either type, or some type in this case. It takes two type arguments, and it has two constructors. Either a constructor for the left type, which is A, or a constructor for the right type. It's a tagged union, if you like to say that. So another example. This is obviously true, and this isn't. But we've got a proof for this proposition, because we can construct this value. It's like an or. If one of these things is true, then we can construct the whole value. And this leads to some very interesting conclusions with logic when you've got the law of the excluded middle, where you got every proposition P or not P is always true. That's a problem, because there are unsolved problems. P equals NP, true or not true? Which proof? We don't know. We can't provide a proof because we don't have a proof for it, and we don't even have a refutation. So that's a problem, and we are going to deal with that. So next thing, implication. So when I've got a proof of something, I can transform it into another proof. So this is, once again, this is a very, very trivial example. So when A is true, it implies that A is true. Big deal. And this is what this type signature says. It's a very trivial theorem, but it's a theorem, nevertheless. So this thing over there is just a lambda. If you know JavaScript, it's when you write function, parents, x, parent, yada, yada. Lots of stuff. We just write backslash. We thought it was better than just writing function. So here we're using that. Pretty simple, once again. You might notice that we're not stating A as a type argument. That is, Idris can figure that out. I was a little bit, well, noisy in the first example. So here you go. So now it's getting weird. Now we're getting into the dependency type land. Since we want to have something like a predicate logic, we want to have quantification, universal quantification, existential quantification, and this is the universal case. So it's just a generalization of the function space. So here, the return type actually depends on the value that we feed into the function. So you can read this one as for all natural numbers, we can say 1 plus n equals n plus 1. That might sound trivial, but we need to prove that. It's mathematics. So natural numbers are defined inductively. It's either 0 or a successor. So in the 0 case, we can say, okay, we can fill in 0 up there. We see 1 equals 1. Okay, reflexivity, we've won. Next thing, we pattern match on the next case. And what I'm using here is I'm calling plus s recursively, and I'm using rewrite to rewrite the goal. It's not that important. I can show it to you after the talk, but we're not going into depth. So this is a proof by induction. So the stuff you learn at school, and I never understood in school, but I understood it with dependent types, which is weird. So it feels natural. I don't know. So just for the sake of completeness, we've got existential quantification. We're not going to talk about that, but I just want to fill you in on this stuff. So recall the vector. The vector has a length of some natural number. And when we filter that, so we've got a Boolean function here that looks at every value and figures out this is true or false. And we throw out elements if they are false. So we don't know what the length is, but we know there exists some natural number that reflects that length. We use this kind of weird tuple there. It's called, some people call this a dependent tuple. Some people call it a dependent product. Some people call that a dependent sum. It's horribly confusing. I like to call them sigma type. Yeah, very helpful. So yeah, this is just, we can say, okay, we can filter this and we know there exists some length. If we filter the empty list, it's obviously going to be the empty list. If we filter some const case, then we call filter recursively and we go through it. Either this is true, then we increment the length by 1. Otherwise, we just throw it away and we don't keep track of that. So this type checks as well. So last thing, negation. I hope I'm not boring you. So this is negation. We want to say when something is not true. Obviously, 2 equals 3 is not true. Yeah. So here I'm convincing Idris that this is not possible. When I'm saying, okay, REFL, this doesn't work. REFL is not a constructor of 2 equals 3. So we have to convince Idris at some point that this is not going to work. So this impossible keyword helps. So whenever we're trying to say that something's not true or negate something, we just say that this proposition implies false. So it's a function. So we have to map every value in the starting set to a value in the image. It's the image, or yeah. If the domain is empty, then we can't map it. Then we can map every point. But if the domain is not empty and the codomain is empty, we've got a problem because we cannot map these types. We cannot build this function. So this is what this negation stuff is about. And now we're going to use that. As I said before, the law of the excluded middle says that every proposition is either true or not true, which is a problem when we've got unsolved problems. So when we want to negate that, we would just say not, this is not true, which would be a very big problem because then we couldn't decide if something was true or not. So in this case, we're saying not, and that's not the classical not. In classical logic, not A is A. So this is it's not that way in constructive logic. So what this is saying is we do not refute the law of the excluded middle. We cannot assume it in general, which is a very important distinction. So this either A, not A is so popular that we got its own type. We call it DEC for decidable. And we will use that in the next example. So live coding. Watch me fail. So let's write a new model. We call this demo. And yeah, so I want to introduce you to a nice little data structure, which is called tree. And it takes a type, and it returns a type. So it's got 2 constructors. It's got a leaf and branch. So tree of A, branch. And it takes a value of A, takes the left-hand tree and the right tree, and returns a tree. So this type checks. So we can type check this in Vim. If you're using Emacs, there is a great Emacs mode. So everyone's served here. So, huh? Excuse me? We just have the list, just have a leaf. It's just a leaf, leaf, branch, whatever. So you can take an empty tree is just a leaf.
But that's not an empty tree. That's a singleton tree.
Whatever. Yeah.
Have a value attached to it.
Yes, it doesn't have a value, therefore we can think of it as an empty tree. So let's build something that we call zip with. And we've got a function from A to B to C. And it takes a tree of A and a tree of B and returns a tree of C. So we put them on top of each other and just, well, apply the function to all the pairs. So yeah. I can say, give me a definition. So this is one of the this is the interactive stuff that I was talking about. Need to do something. I need to help the compiler a little bit here. Excuse me. So let's be. So I'm just telling Idris, please choose these names because Idris is terrible at choosing names. It's horrible, really. Trust me. So what I can do now is I can do pattern matching. I can, but in this case, I can do case splitting. So give me all the cases that T1 can have. It can have two cases. Can have leaf or branch. So yeah, cool. Let's keep going. So case split. Okay, this works. Okay, these things are called holds or meta variables. It's a part of the program that we didn't write yet. And we can ask Idris, what type does it have? So this is what we know. We know these things. This is where we want to get. So I can ask Idris, can you solve this program? Can you solve that for me? And in this case, it could. But what happens if we got this case? So we can throw away data. That might be the tactic that we want to use in some cases, but in other cases that might be bad because we're losing information. We don't want to have that. So this is kind of bad. We don't want that. We don't want these two cases to happen. So because we're losing information here. So what I'm going to do is I'm going to introduce a new type, which is called a tree shape. And it's just a type. And let's call this a leaf shape, which is a tree shape. And the branch shape, which takes a tree shape, and it's a tree shape. So this is the shape of the left and the right branch. Let's throw this one away. And take a tree shape here. So this has, obviously, leaf shape. This has some shape S prime, and it will take a branch shape of S and S prime. So yeah, once again, zip with C. So now I'm ensuring that these trees are going to have the same shape. Oh, this is wrong, so this is better. Okay. Obviously, this is going to type check. Yeah, that's nice. So now we can do case splitting once again. Case split here, case split there, and lo and behold, the other cases, they don't show up anymore. Because Idris figured out if this one's a leaf, then this has to be a leaf as well. Same goes for the branch. Because they all got the same shape. We statically guaranteed that these shapes got to be the same. So now this is getting pretty nice. So in Haskell, you've got something that's called type inference, where you can write a program and Haskell can infer the type. We can't do that in dependently typed languages, but we can do something else. You can say, write this program. Idris said, okay, that's leaf. Can it do this? This looks pretty tricky. Yes, it can do that. So this is pretty neat. Once we've got enough information at the type level. I can sympathize. This blew me out of the water when I saw that first. This is so great work, Adrian. Agda is even better at that. But yeah, so Idris can figure out this by the information that it's got there. So it can look at that. So it's a lot of information. Could have written this by hand. but we don't need to. That's pretty nice. So let's prove something. Let's write a function, and we call this one is elem, and we want to check if an element is in the tree. And I'm going to gloss over this detail for a second, so bear with me, please. So we've got some element of x of type A. We've got a tree T, which has some shape S, and it has elements of things. So what could be the result type that we want here? In a lot of languages, we'd say, okay, this is a Boolean, but that's a little bit problematic because a Boolean doesn't really convey any information. It's just saying yes or no. It's like the answer is 42. What's the question? It's not very helpful. So what I want to do now is I want to write a predicate that contains a lot more information than just the Boolean. In the case of the Boolean, I could just write false for every case. So I could write a wrong function here. So let's write a predicate. We call this isElem, and it looks like this. So let me look on my cheat sheet here. X, and look at the branch, and the left tree and the right tree. So this is a proof that we found the element. So we're not saying we're not just saying, okay, we found the element, but we are constructing a path to find this element. So this is the proof that we found it. Obviously, we need the paths. So if we know that X is in the left branch, then we can say it's in this tree. Oh, what are you doing there? It's hating me. So let me look at the error message again. Unexpected end of file signature. What is oh yeah. Oh, so say hello to the deck type again. So we can decide this problem. We can say for all elements x of type A for some tree, we can decide if the element is in there. This is why I introduced the deck type anyway. So obviously we need the right branch. Can't type. So is element. Please type check. Yeah. Yeah. We get to that later, okay? So can an element be in a leaf? So look at the constructor.
According to your definition of there, yes.
No, it can't. So the branch, that's a good. You can a branch. Yeah, the leaf doesn't have an element. That's what I meant with empty tree. It doesn't have any elements in this case. Oh, can be a little bit smarter here.
But in the tree declaration, it does say A.
Yeah, because it's a tree of A.
In the leaf declaration.
In the leaf declaration. But yeah, because it's a tree of A. But it doesn't have any elements. Yeah. It's an empty tree of type A, whatever A is. So let's case split here. And let's find out what we want here. So obviously there cannot be an element in this thing because leaf doesn't have any values in there. So what I'm going to write now is a function that says not in leaf. So yeah. And I'm going to extract the lemma. So let me get rid of this. Sometimes Idris is very just wants to add a lot of arguments. So okay, let's just do not in leaf. Excuse me, here, and this is just impossible. This is once again. So in this case, this thing doesn't have any elements, therefore it cannot have x in it. So this proof says can't be in there. Let's call this R. Yeah, and the type checks. So we can write here, this is just the same thing. Let's make this a little bit prettier. So now we've got to prove that in a leaf there can't be any elements. So we got a refutation for that. So let's do something else. What I'm going to do now is I'm going to do something that's called a with pattern, which is an intermediate computation. And now I'm going to use this DEC. So this is a type class that says for type A we can decide if two things are equal. So there are some things that we cannot prove to be equal. It's a little bit bothersome, but yeah, they exist. So we can do case splitting once again. Case splitting once again. And look at that. So this is Y. And once I'm doing pattern matching here, it turns into X. So it figured out that these two elements got to be the same, because we've got a proof for that. This is dependent pattern matching, or nonlinear pattern matching. So let's once again try to find a proof. And here's the proof. So writing these things is utterly boring. This is got this written down somewhere. So yeah, this is, oh, damn it. So, oh, it didn't load it. Bummer. Nope. That's just an address. It's nothing interesting, really. So sources, Idris, 31C3, examples tree, IDR. So this is damn it. Vim, you're failing me. So this is the whole thing. And I don't want to write that. This is just utterly boring. Most of Idris writes this for you. So what we got here is we got a proof that we didn't find the value in the leaf, we didn't find a value in the left branch, and we didn't find a value in the right branch. And this is a proof that it's not. 4 minutes, 40, 50 minutes, okay. So this is a proof that it's not in the tree. So that's what I told you. It's a decidable problem, whether that thing is in the tree or not. So yeah, that was live coding. And now I want to talk a little bit about effects. So until now, we didn't do any side effects. And if you know Haskell, there is this bad M word I'm not going to mention here. People tend to get scared every time I say that. So we've got something that's called algebraic effects. I don't know if this sounds less scary. I don't think so. So this is a very dumb program, but nevertheless, it has some interesting things to tell us. So up there, this is a very horrible-looking type signature, but that's in fact the type signature. So in Idris, we write type signatures that are bigger than the program sometimes. That feels kind of weird, but okay. So what this notation says, we've got two effects. We've got file I/O and we've got standard I/O. So we can use the file I/O effect to work with the file system. We can open files, read files, delete files, whatever. Standard I/O is just write something to the console. So nothing special here. And we can put them into this list. So we can have a very expressive type signature. This type signature tells us what can go on. So in Haskell, there is this I/O type, and it can pretty much do everything. So it can communicate with the outside world, or calculate pi, delete your hard drive, whatever. So in this case, we just know, okay, it's file I/O. It can do some stuff on the file system, and it can write to the console, or read from the console. So this type signature has a very interesting, have this open, has a very interesting type signature, this function, open. Recognize that? If then else on the type level. And what it does is actually figures out, could we open the file? If yes, then we've got an open file handle. Otherwise, we don't have one. So this is where we want to use something like if and else on the type level. So if we look at this effects example once again, we are pattern matching on the result. Is this a successful operation? In this case, yeah, we can read from this. So let me try to compile that. P effects, I'm not doing that. Takes a lot of time. It does a lot of things. And the compiler needs to get faster. So it just reads in the first line of this program, of the source code. So module main, yeah. So what happens if we do something like that? We're not closing the file. Try to compile that. And now it's complaining. It says it went wrong, basically. We are working on something that's called error reflection, which makes this stuff readable. But if you squint a little bit, you might be able to read it. Or if you're just using Idris for a very long time. But what this actually says, it's, okay, you promised me that this thing would be closed once you leave the program. I didn't do that. So it's still an open file handle. So we can track if files are open. It's one of these things that happen quite a lot. So you query the database and you just leave that open and you run all file handles and your application crashes and everyone's sad. And yeah, so you can check that. We can check that at compile time. We could also do something like that. We could just try it. Read from a closed file. So yeah, this is going to spit something else out that you're probably not able to read. I can't do that as well. So yeah, so this is pretty useful. And I want to show you something that is even more useful. Maybe not too much, but so this is a little demo that does typed CSV. So we read in CSV and look at the schema, just the header file, and look at, okay, what columns do we have? And read that in, and we do that at compile time. So once we compile this program, it goes out, reads in the file, picks out the header, and generates a schema. And what's interesting about that is, so yeah, this is Pokemon, so. So this says, okay, read in the file, read in my CSV, pick out the header, generate a schema, call this one test schema, and whenever we add a new row to this, or we want to query that, we've got compile time guarantees that this value is actually in the CSV. So we don't have to check, is it in there? This will always succeed. I'm going a little bit over the top with this because I'm also stating the amount of rows that I'm reading in, which is a little bit too much to be practical, but it's just, yeah, for fun. So yeah, let me show that to you. Let's go to CSV. So let's compile that. That takes even longer. Yeah, that took quite some time. So yeah, it's Shiggy. It's German Pokemon, I'm sorry. So let me query something else which isn't there. Don't fail on me, Idris. Yeah, and say, okay, this is not element of the schema. We couldn't solve that. You might recognize this is element thing, which is over here in is elem. So this should look familiar somehow, and that's pretty neat. So this line constructs such a proof automatically. So we don't want to write there, here. That's a dumb task. So that a compiler can do that. So this is what this proof search is doing. So whenever we are looking up some field f in some schema, we just try to find the proof that it's in there, and then return a result. So yeah, 10 minutes. I think I'm done here. So if you want to ask me questions, please go ahead.
Well, my mind is still blown, but if you have questions, line up in front of the microphone and ask away.
Let's grill the speaker.
Microphone 1.
Okay, so thank you for your talk. It was interesting.
Thank you.
I have a question. Is it possible to make error look better? I mean, to detect some example type mismatch and write that the file was not closed in that case?
That's possible. So someone's working on this thing called error reflection, and it gives you a type structure, a data structure that represents this error, and you can write an Idris program that interprets that error message and gives you something that a human can actually read.
Oh, cool.
So
Thanks.
So this is one of the things why dependent types are research. We don't really know how to handle this stuff. It's very hard to write big applications in Idris at the moment.
Okay, over to Mike 2.
Yeah.
Hey, how is Idris implemented? Is it running in a VM? Is it self-hosted?
It's not self-hosted at the moment. It's written in Haskell. So I love Haskell. So it's a great language. So we are planning to rewrite it maybe at some point. But there are not a lot of things in place that we need. So we've got this parser library called Lightyear, which is a pun on parsec from Haskell. And this is what I'm using in this CSV parser. So we need stuff like that. We need when you look at the Idris interpreter or the compiler, it has a lot of dependencies, and we are not nearly there. So maybe at some point we'll be self-hosted. But it's not priority.
But so what is it? So the compiler generates.
The compiler generates C and puts it into GCC.
Okay.
So or it generates JavaScript or whatever.
Okay, right.
Yeah.
Mike 1.
Okay.
I have two questions actually.
Okay.
First one, do you have any? Are there any projects that you know of that try to apply this dependent typing to imperative programming languages as opposed to functional?
Excuse me, I didn't get that.
Are there any experiments trying to port dependent typing to imperative programming languages?
I know of a project that's called Flow that is written by Facebook. It's something that does statically checking on JavaScript, and I've seen some of the ideas. So this branches, if then else branches, it knows in which part of the branch it is, and I don't know if it really qualifies as being dependently typed. I don't think so, but there is a project that tries to bring dependent types to JavaScript as well. Scala actually has dependent types. It's pretty much the first commercial programming language that offers dependent types, even though not full dependent types like we have in Idris, but something that is pretty powerful.
Okay, next question. The example of the trees, where you have this tree shape type. How is that actually implemented? Do you have for every tree shape one runtime object? And if you construct a new tree, you have to for every tree node construct a new tree shape.
You don't need these tree shapes at runtime. They can get erased. So you don't need to store your indices. So you don't have to carry around the length of the vector as well. So it just
are you sure?
Yeah.
Isn't that needed for error
detection? There's a paper on that by Edwin Brady that's called how is it called? Like something like inductive families don't need to carry their indices or something like that. I don't know. It's something like that. You can't erase them. You don't need to. Sometimes you carry them around when you want to inspect them at runtime, but you don't need them in general.
Okay, over to Mike 3.
Quick question, is it as lazy as Haskell?
No, it's strict. So we've got a strict a lazy constructor. You can put laziness annotations, and but it's a strict language. So this is geared toward system programming, and Edwin wanted to have something that is actually strict. So you can reason about space and stuff like that easier. So, yeah.
Mike 2?
Yeah, just a question about these types and proofs that you seem to have. I'm intrigued. Does this do only propagation or fact propagation to get the things that you see there when it comes up with definitions, etc.? Or does it do conflicts? In other words, does it do an NP complete search and aborts eventually when it's sort of like, oh well, I've been researching for half an hour and I'm not going to come up with this definition anymore? Or do you only do propagation of facts like LLVM? All the current compilers. Let's put it that way.
So I think that's a question that probably Edwin should answer. I don't think I know the answer to this. I'm sorry.
Okay.
So,
no.
Okay.
Mike 1?
Yeah, so I got two questions also. First one is, you showed some first-order logic, existential and universal quantifiers. Can you do also second-order logic? So quantifiers and sets, or is that beyond the scope of the language?
Didn't get that as well, sorry.
So can you do second-order logic also, or is it just first-order? Also modal logic, is that temporal modal logic, or?
Oh, that's a good question. I don't know. so grilling me
I'll
here.
have to try. Right.
Maybe.
And also the second question is, you show this CSV example, and it seemed like, do you actually need to have the input CSV available for compiling?
Yeah.
So that's,
you have to have that. You can use this in another nice example would be tables for a database. Mm-hmm. So you can call the database, get the schema, and type it there. So the CSV is obviously it's just an example. It's not really something that is super useful, but I think it's a neat example to just demo a little bit of the stuff.
So what happens if you feed it with a different CSV?
And then you need to compile that once again. Yeah, this is so it can't change the program magically. Just it's compile time.
Okay, so you need to actually check the inputs somehow before running it. If
the schema changes, you need to change. You need to recompile. Yeah.
Signal Angel, do we have any questions from IRC and stuff?
No. Okay.
Mike 3?
Yeah, so in that example with the file handles, is the implication of that you could not, with the given types, write a program that has too difficult logic governing whether the file handle is in fact closed? Or is it that compilation might in fact not terminate?
Good question. No, it's not. It's not really that. So the type system just forces you to handle these two cases. So you're not actually compiling, and the file handle doesn't get opened during compilation. So
no, that's not what I mean.
Okay.
I mean, what if basically, presumably, you have a certain logic which is captured by this type system, which it might or might not be decidable. And if it's decidable, it probably means that you cannot prove things that are particularly complicated about programs, or cannot prove the termination of particularly complicated programs.
So you cannot. Is
the type system decidable? Is what I'm ultimately asking.
Is the type system decidable? I think that should be. It's not.
Dependent type checking.
Dependent type checking is. I think there is a paper that says it's not decidable, but I'm on very thin ice here. This is so you're asking theoretical questions. I'm just some compiler, wannabe hacker. I'm not too deep into the theory. No, this is perfectly fine. Yeah.
Mike 2, please.
Well, if you use first order logic, then it's not decidable.
If you have a question, please come to a mic.
So he's got the answer to your question, I think so. Yeah. So we can take this conversation
offline. Can you go to a microphone, please, so it's in the recordings?
I have a question regarding the example for the file handling, closing of the file handlers, where there is an error if the file is not closed.
Yeah.
And is it possible to generate the closed statement automatically? So to satisfy that the file is closed at the end.
That's automatically closing that thing.
Yes.
That's a good question. I don't know. But It might be possible.
Because the same thing can be applied to the memory management or resource management in general.
Yeah. I don't know. I haven't tried that. Could be possible. Probably.
Thanks.
So let's find out, maybe. Just tag on it. Okay.
Last question, mic 3.
Is this language only a proof of concept, or do you plan to support it a longer time? And what are your plans to implement next?
So this is once again a question that should be best asked to anyone, but we talked about this quite a lot. This is an experiment. There are a lot of different approaches to dependent types. There are a lot of different kinds of type theory, like intentional type theory, extensional type theory, observational type theory. People try to come up with all sorts of different approaches there, and Idris is pretty conservative in its approaches. So it's just one way. Maybe Idris will turn into a programming language that can use in production, I don't know, 10 years, I don't know. Maybe never. So currently this is just a fun project to find out where we're going with that. And we can go with that.
Thanks.
Yeah, sure.
Well, on a housekeeping note, if you're leaving, take anything with you, and a round of applause for Raichu.
Thanks for your attention.